Good afternoon, everybody. So I guess I've really got the tough job today, huh? Probably the toughest one to keep everybody awake. Thank you. All right, let me see. Hopefully I can do that. The presentation today is going to be about accelerating the RISC-V revolution, unleashing custom silicon with specific design platforms and custom accelerators. So let me dive right into it and see if I can achieve my goal of having everybody sustain long enough and ask some questions at the end. So really, let me start in a slightly different way. The question that I'm asking here is, how did Instagram turn into a $1 billion company with just 13 employees? And obviously, that's a rhetorical question. We all know that. It's a very tough thing to do, especially when you consider if there really have been any billion-dollar companies with 13 people in the hardware world. And it's a good question to ask as to why that is not the case. What is it that allows people in the software industry, somebody making a photo sharing app, to be able to get to $1 billion in valuation, and a lot of us seemingly hardworking people in the hardware world don't seem to be able to get that so easily. Yeah. And one of the reasons why, actually there are two reasons why I think this happened. One key reason why this happened was that those 13 people didn't do it alone. There was an army, an ecosystem, a whole country, citizens' world around it to be able to develop all the things that was needed to make that simple photo sharing app. So if you look at Instagram's tech stack, and a lot of these names are probably familiar to many of the folks in the software world, these were things, whether it's Python or Ubuntu or SQL databases, stuff like that, were not made by Instagram. If they had to do everything from scratch, obviously they would have had 13 plus a couple of zeros after that number of people, right? And the same thing as from an infrastructure perspective, thanks to Amazon and the good stuff they've been doing for the last few years. They used Amazon Web Services, and they probably never had to buy a single server before they did that. And so what we're trying to attempt to do here is really take RISC-V and see if we can use the platform that has been created, fortunately for us, started about 10 years ago and very well described by Rick earlier, and see if we can take advantage of that and really make it into this open source technology that can eventually help us make chips a lot easier, faster, better, without everybody having to invent the wheel. And so definitely SiFive is committed to that, and we're moving down that platform pretty heavily. Recently, NVIDIA announced that they've taken their DLA, the inference engine, and open sourced that. And I'm sure more and more of these announcements will come about, and more people start doing more of these things. And the place where SiFive gets involved in all of this is really we're trying to take this and offer that infrastructure piece through our SiFive cloud services. And I'll tell you a little bit about what this is in a moment. Okay. So what is SiFive Cloud Services? What we're really trying to do here is take the CPUs as a soft IP. Around the core, as somebody earlier said, the core is nothing. You need a system around it. So build that system around it and have an ability to do prototype ASICs and eventual production ASICs in a seamless manner, realistically using the cloud. Now, this seems like a very, very far-fetched idea. Today, everybody is buying these heavy-handed tools. You're buying lots of servers, lots of equipment. You have armies of engineers who are making these chips. The holy grail here would literally be to be able to take some basic ideas, take some basic templates, press a button, and pronto, here comes the chip. Hopefully somewhere down the line we'll get there, but it'll be a hard and long journey, but that's a goal. So to that goal, the place where SiFive is starting is, fortunately, we've been lucky enough to have been part of the early adopters of the RISC-V ISA, and using that, we've got a couple of platforms already created and ready. So those platforms on the CPU side, there are two of these. This Freedom Everywhere platform, which is a low-power 32-bit microcontroller class platform, and the Freedom Unleashed platform, which is a high-performance 64-bit multi-core application primarily for Unix and Unix-based systems. And I'll tell you a little bit more about these two platforms in a minute. But using these two platforms, then eventually a person who wants to design a chip can start with one of these, depending on the type of chip you're making. Add to that a list of IPs that have already been onboarded, available in a manner that can be actually easy to pick and place and drop into your system. And for that, we have come up with this concept of design share IPs. Today, we've got companies like Rambus, Ultra SoC, FlexLogic, eMemory, a bunch of other folks that have joined. Very recently, from India, Terminus Circuits has also joined this bandwagon. So now all these IPs are going to be available as part of design share, and that allows then the customer to add their IP, maybe some additional open source IP, and use the cloud services to actually create a chip. So this is the concept, this is the idea, the ability to take that hope that was created using the RISC-V ISA 10 years ago, and now create it into a real tangible reality where doing chips in an open source environment and manner becomes easy for everybody to do. Literally, we're hoping that this, and that's what all of us here really want to do, is to be able to do more and more chips using the RISC-V architecture, really drive innovation, have more and more companies grow to make different applications, and not be dependent on a particular hardware, right? And be able to do your own hardware in a very simplified and easy manner. So the very first, what we call templates that SiFive has already created is a Freedom Everywhere template. You can see the block diagram on the left. There is a E3 core complex, which is basically 320 megahertz SiFive E3 CPU. We've heard in some of the earlier presentations the CPU has been used, and tomorrow you'll hear a little bit more about it as well. It has multiple low power domains, low power standby, wide range of clocks, and it's primarily a microcontroller class core complex along with the slow peripherals. This chip was taped out on TSMC 180 nanometer and is now available in silicon. This platform was eventually put into an Arduino-compatible RISC-V development board, which we call the FE310G000, and today that's available to buy from crowdsupply.com. And actually, we're selling this in about 160 some countries, and there have been at least over 1,000 purchases of this board where people are using it. And since it is one of the earlier implementations of RISC-V core in a hardware and has been available with software, et cetera, for a while, I think this is sort of a first implementation of what can be done with it. Having said that, when sort of RISC-V initially came about, a lot of people were kind of thinking of it as a microcontroller, sort of M-class CPU, and not really something that might eventually be something beefy and for people to start looking at it very seriously, in being able to actually use Linux and Unix and all the kind of fancy stuff and put it in applications which are a little more heavyweight. And that's really what SiFive has done next, is we've come up more recently with Freedom Unleashed 64-bit multi-core RISC-V Linux platform. So this particular device is made using the U54 multi-core complex. It actually has a quad-core environment with a single E51 core, which is more for control processing, and the quad-core stuff is more for the heavy lifting data processing. It comes with a cache-coherent tile link with banked L2 caches. And so this particular chip runs at 1.5 gigahertz in a TSMC 28 nanometer process node. This has been taped out. The silicon is back. It's what you're seeing here. It's been put on a board, and I'll show that to you shortly. So it is a real implementation of a 64-bit in silicon high-performance CPU complex, which is available. To this, we've added some of the standard processes and IPs that are available from our design share platform, and created a chip that eventually can be used in some very interesting applications, and I'll get into that in a bit. One very important part of this design is what you probably see more towards the middle portion of the block diagram, is this FPGA block. So what we've done is, the box on the left side, which is titled at the FU500 base platform, hopefully you can see that name there, that's the chip. And we have taken the tile link infrastructure, which is again part of the standard open source community, and created a chip link out of that. So it really extends your tile link bus into an 8 gigabit per second data bus going off chip. And then this connects to an external board with an FPGA on it. And so that allows this architecture to be extended into multiple applications, a variety of use cases, if you will, where this can be used. So this chip was, of course, eventually put on a board. It's called the SiFive Unleashed board, which is really the world's first multi-core RISC-V Linux board, and which is available today. The boards that were initially put on crowd supply have all been, unfortunately, sold out. But there are more that are coming up, hopefully in the Q4 timeframe, so you'll be able to buy it and use it for some heavyweight chip development. All right. We've also taken this core and done some performance analysis with similar cores or similar products from companies making similar chips. So an A53 all-winner product at 1.2 gigahertz, and an A53 1.5 gigahertz rock chip product, right? And our SiFive FU 540 ASIC. Now, if you look at it, the platforms are similar. The major difference between a U54 and A53 is the U54 is a single issue CPU, whereas an A53 is a dual issue CPU. And even keeping that in mind, if you look at all these performance numbers as you go across the board, you'll see that the SiFive RISC-V processor actually comes pretty close to achieving a very similar performance metrics as a very heavyweight A53. The spec in 2006 numbers with SiFive CPU at about 3.6, the A53 rock chip is about 4. So it's close. The one number in the middle, the lib quantum number, doesn't look that great. From my understanding from the engineering team is that it's more got to do with the compilers, so that needs a little bit of work. Some of it which may be done internally and some by the open community that's out there. So I think performance-wise also what we're seeing is that here's a CPU that's probably been around maybe 3 years at best in a form that's usable with the support of the community compared to an ARM V8 architecture that's been around for a lot longer with millions and millions of lines of code and millions of hours of engineering support. And we're coming pretty close. So when I think of it in sort of an India context, I was almost thinking of it like you guys have heard of Reliance Jio, right? The way they were able to come in recently in the last few years and really take over the whole mobile infrastructure space was because they did something radically different. They decided, I'm not going to support 2G and 3G, I'm just going to support 4G. Right? It seemed like a ridiculous idea, but to some extent, the way Reliance Jio has caught up, I mean, if I asked you guys, how many guys own a Reliance Jio phone or data plan here? There's quite a few here, right? So that tells you that they were able to do this in a remarkable way with a brand new thought process, which is what we're all trying to do here with the RISC-V architecture. Okay. Now, to take this to the next level, Microsemi, one of our partners, has actually made an expansion board which allows us to take the basic SiFive Unleashed board and make it into a PC. Right? So on this expansion board, there is a PCI root capability that's available, and through that you can connect extra add-in cards for disk drives, SSDs, audio, network controllers, etc. And literally that's what we have done is we've taken this expansion board, which is again available for anyone to use or buy, and created a PC out of it. In this, there is the Microsemi PolarFire FPGA also available, so you can actually take your custom RTL and add it to this. So really going back to the earlier block diagram that we were talking about, where it says your IP block, that's really the FPGA. That's connected on the other side of the PCI Express switch. So this allows you the flexibility of literally dropping in whatever RTL block that you may need, and I'll show you an example of which RTL block we've dropped in here as a use case. But now you take this and you make it into a PC, and the Linux community out there, apparently there is a software, I'm not a software expert, so maybe I'm mispronouncing some of these terms, but they've taken a Debian image and used that to create a PC on this. And this was the SiFive website, which was the first sort of image that came up while all the fingers in that room were crossed, and finally it's working. So it's pretty cool that you're able to actually run this and browse. What's even more cool is that now you can run Google Maps on it, which means you're actually running things like Java behind the scenes on a regular RISC-V 64-bit architecture. And this is not stuff, again, going back to the Instagram example, that was developed all in-house at SiFive, because obviously we couldn't have done it. But it was stuff that came from the community that we were able to use and have this thing running. So, of course, the engineers felt that you couldn't get cooler than this. But when you give them a challenge, they always figure out that there is more stuff you can do on it. So that's a picture of Palmer. He's one of our software engineers. And what you see in this is a webcam attached now to that same expansion board. And you really have a complete multiprocessing environment being used as a multiprocessing environment, where you have a webcam showing an image of our software engineer. You have his Twitter account where he's sending messages to whomever while playing a game. So indeed, what the infrastructure that Rockchip and Allwinner had for a long time, and depending on the CPU architectures and software code that had been written for decades, was now something that we were able to do in a matter of a couple of years. In fact, I would say maybe even less than that, because a lot of the software that has been written on this platform has happened maybe in the last 12 months or so. Right? And I think that's really the power of an open source architecture, which we all believe will really shape the way things are going to happen in the future. And here is another example. So we took this to the next level. I talked about that FPGA that was available. We actually worked with a company called ADS. That company has an inference engine. That inference engine was ported into that FPGA as an RTL code, as a hardware accelerator. And that's really the promise of what SiFive is being able to provide here is you've got the CPU core platform, which can be customized to whatever level you need. There were examples of people wanting to do hardware accelerators, do custom instructions, build custom CPU cores based on the amount of cache you need or the amount of pipeline you want or whatever else you need. The flexibility is all there. And on top of that, add this accelerator, and voila, you have something that actually works. So this is a working inference engine on the same platform. And through our graphics card, we're drawing these yellow boxes to point out what these things are and show that you can actually make an edge AI ML device, which seems to be right now, talking to anybody, the flavor of the season. Everybody feels that there has to be a need to build edge device, which I think is the way going into the future. And we have working silicon that shows it can be done on a RISC-V platform. But that was all digital stuff. Now what we want to do is we want to expand this platform to not just digital stuff, because at the end of the day, all these chips have to touch and feel and get sensor information from all kinds of things. And at the end of the day, that world is an analog world. Now, how do you take an analog world and put it into a similar platform? And so to prove that, we worked with a company called OnChip. They had a bunch of analog IP, which they really wanted to use in a microcontroller environment. We've taken that analog IP, ported it into 180 nanometer with the help of OnChip, and created this platform, ASIC, that you can see, which actually uses the E31 core complex as the base CPU based on the RISC-V architecture, and then all the analog components that you need. Now, these components eventually will be on a design share-like environment, so that if somebody wants to build a chip using the SiFive cloud services, you have these components that are available out there, construct your CPU, construct your core complex, get these analog components or whatever the components you may need, and create your chip. So it is not just about a chip with a concept, a pie-in-the-sky idea. It's about chips that actually can work, are going to be used in actual real applications. Unfortunately, of course, when it comes to analog, a lot of the analog stuff is going to be related and tied to the process technology. So it's not an IP that you can just download and use it as and when you need it. So in that sense, it's not true open source. You're not going to find it on GitHub or something. But at the end of the day, at least it's available through the design share platform. The GDS2 will be hidden because TSMC will not allow anybody to expose it freely. But it can be used in making ASICs. So coming to the next couple of things that is to, so where do we want to take all this stuff? How do we move forward? Part of SiFive is obviously, we're a commercial company, we want to do something in that front. But at the same time, part of it is also to evangelize the RISC-V architecture and have more and more people use it. That's what, at the end of the day, all of us want. So to that effect, we are really trying to democratize this idea and give an option to anybody that's out there willing to spend some time on creating some ideas using the RISC-V platform to come up with some ideas, suggest an accelerator, a co-processor, some other IP that you may have or an idea that you may have. Submit that idea to us on the website below, or you can go to SiFive.com website, and by October 31st, you can submit it. And then based on this, we're planning to pick a partner, and in the RISC-V workshop in Santa Clara in December, announce a person that we feel would be a good partner for us in this endeavor, and then actually put that into a chip and make a test chip using it. So anybody out there, please use this as an opportunity, especially for a lot of students or people from a startup community that want to get on a bandwagon without having to spend too much investment. Here you have a platform with which you can get your ideas into silicon fairly easily. In addition to that, everybody's heard that, of course, India has adopted the RISC-V as the national ISA. And so as part of that, SiFive is rolling out a 6-city tour throughout India to talk to the engineering and student community about RISC-V. This is going to happen in the end of August. I've got the dates and the different cities that we're going to be part of. Of course, this information is available on the SiFive.com website as well. So certainly for those people who are in Chennai, make sure that you attend the session that we have on Friday, August 24th, so about 5 weeks from now. And then if you're in other cities or want to visit some of the other cities and you can join us, it would be fabulous. Okay, we're going to get some speakers, especially some of the people who have created the RISC-V platform, probably Kriste Asanovic, as well as Jan Sapli may be coming here, and you'll get a chance to talk to them or meet them as well. So with that, I'll come to the last summary page of my presentation. Really would like everybody to join the RISC-V revolution. We have released the HiFive Unleashed platform as a important milestone for the RISC-V development. It's important for the software ecosystem and certainly for development, education, hardware prototyping, whatever you would like to do with it. Certainly a great venue or avenue for the researchers and entrepreneurs to be able to really use the RISC-V platform. Now you can indeed make a custom chip using your platform because there is that FPGA that's available using it. And this then forms the basis of you going in and making your own ASICs or custom silicon, right? And then finally, of course, you have the option of providing us your keen ideas and joining us, partnering with us on putting it onto a real silicon platform. So with that, I'll come to the end of my presentation. Thank you.
Ignatius from Santa Clara. I was a little confused about your analog cells. I thought it was 0.18, and I thought maybe 1.8 volts, and you said 3 volts.
Yes, so the analog cells, the core voltage will be 1.8 volts. But on the IO voltage side, they'll be 3.3 volts.
Okay, thank you.
Sure.
Yeah, so one question from here right side.
Okay, yeah, go ahead.
So we are interested on that SiFive expansion board. Mm-hmm. Is it available today to buy from crowdsupply.com?
Yes, so I believe the expansion board is available, but unfortunately, as I said, we're sold out of the main HiFive Unleashed board. Okay. But I think if you just check in about 4 weeks or so, there should be some ability to pre-order again, and okay, they'll be available in the Q4 timeframe.
Okay, thank
Certainly,
you.
So you can use it for building your Unix systems.
Okay, thank you.
And can you give an example of how?
Sorry, yes.
Can you give an example of how someone is using the Silicon cloud services which you are selling?
Okay, so right now we're in the process of putting that together. The chip that you've seen, the 28 nanometer design that we taped out, we're internally taking that and going through the motions of developing the entire chip on the cloud. Once that's ready and will be launched soon, the idea is that you would actually go to the SiFive.com website, log in there, decide which of these, the Freedom Everywhere or the Freedom Unleashed, these are the two platforms available today. Eventually, we'll add more to it, you want to use. And then using that, go to the design share, decide which IP additionally you want in addition to the CPU core complex. Target a particular fab. In this case, the fab and package will have some limited number of options available. And then you could prototype a chip. And if that prototype looks good, you can go to production with it.
So is it more like a marketplace or a real cloud?
No, it is a cloud. It is an actual cloud. The marketplace place comes in from the design share concept. So anybody that wants to join the design share bandwagon is most welcome to. Anyone that has IP, either soft IP or hard IP, that they want to share with the community, they can do it. And then there are, of course, certain commercial models that will be there eventually as part of that.
Yeah, one question on the FPGA part.
Sure.
How easy it is to do your custom RTL and plug it in there? Are there tools available to do this today?
Absolutely. So Microsemi, as you know, sells FPGAs along with the hardware. You'll get a bunch of software that's available to synthesize, partition FPGAs. So you primarily take your RTL code and use the Microsemi tools to create a bit stream that could be targeted to the polar fire.
And how easy it is for the FPGA to talk back to the CPU and have the interaction going on between the two?
Sure. So the FPGA comes with a PCI endpoint. So that allows us to have the chip link talk to the PCI endpoint and to any other hardware that you need. On the other side of the PCI Express endpoint, you also have, along with the FPGA, your other additional USB interfaces, additional PCI interfaces for expansion cards like a graphics card or a display card or that the camera that I showed you earlier. Yep.
Thank you.
Hello?
Yes, go ahead.
Yeah. So in the cloud services, you are just to explain. So who will do the back-end design and all when you want to release the chip?
That is part of the cloud services.
Tools also?
Yes.
What you're saying is the customer has to come to you, select it, and you will do the back-end design, everything, and release the chip for the customer.
Well,
is it that way?
Well, let me just rephrase that. The goal here would eventually be that we don't want to do it. It's the cloud. It's a service. So the tools that are running behind on the cloud would be the ones actually doing it, and you're driving those tools. So the users would be driving those tools that are available on the cloud.
So the user needs to have an experience or expertise in this back-end design or ASIC design. That's what I'm specifically asking, because that is a different domain, right?
Yeah, no.
Processor architecture is one thing, and doing the synthesis, place and route, and things like that, you need capability in a gamut of tools. So the person who is coming to you or the company which is coming to you, do you expect them to have that kind of expertise, or you do it at the back end for them?
Yeah, the idea is that you don't need to have that expertise. That the back end piece will be done on the cloud without necessarily you being experts in that area. Because these are template-based designs, obviously you can't take any generic design and go there. So as long as it fits within a particular template, they should be able to do it.
Okay, thank you.
So this is the same continuation of the same thing.
Sure.
The IPs that are available in the marketplace, how will it be in terms of, say, commercial angle for that, and when the really chip is made and somebody has to get the money paid for the IPs? That
Yes,
doing,
absolutely.
right?
So we're still working on those things. It's not announced yet.
Okay, thank you.
Certainly.